Hello, hello. Come on in, everyone.
I have a question.
How you doing?
I have a test today at 3 o'clock. Is it okay if I leave lab early?
Yeah, I suspect the lab will be finished so fast you will be done by then.
Okay, thank you.
No problem. It's a photoelectric lab, and that'll be our last lab this semester. And next week we'll use the lab period as a opportunity for you all to ask me questions, but it's not mandatory. It's going to be voluntary attendance, so no lost points or anything like that.
Quick question about
Okay.
this past lab. Did I interrupt somebody? It sounded like I did.
She was just answering. She was confirming what I said, but you can go ahead.
Okay. Quick question about this lab. Was there like a bunch of typos on it where it was supposed to be micro? Because it kept asking for the micro F value, but I'm pretty sure it was meaning the micro C value.
Yeah, well, it's micro C in the sense that it's capacitance, but the unit that we use for capacitance is a farad. So that might have not have been one, but I would agree that probably there was a load of typos on it because I'm the one that made it. So I wouldn't be surprised by that. If you have any problems that it makes you not understand something, then ask me, and I can give you a little bit more time to turn it in to make sure it's right.
Okay, I mean, I submitted it, but it was in the units of micro C based off of the last question, just because it was a little bit confusing.
You were talking about the charge, then yeah, it should have been micro coulomb. So yeah, you'd be right on that case.
Yeah, the entire third portion where it's talking about the voltage and the charge.
Yeah.
It was all in the actual text of the question. It was wrote in as micro F, but I had gone in and changed it manually, assuming that that's what we were looking for, because micro F would be a constant value of 1 that whole time.
Exactly. Yeah.
So I went in and changed it. But just for your awareness, in the text, it says micro F for the entire question.
Gotcha. All right, I just made a note of that, so I won't forget it.
Okay.
Appreciate that. Anyone else?
And then about the mastering engineering labs, homeworks. Is there all the dates say December 15th?
Yeah, basically everything from here on out is going to be due December 15th.
Okay.
So I
just wanted to double check that.
Yeah, today I'm probably going to finish up chapter 19, and I'll mention enough of 20 for you to make sense of it. I just want you really for chapter 20. I might even make the homework if I have any for chapter 20. I might make that extra credit as well, because really I just want you to know what the second law of thermodynamics is, so you can, in various forms, and there's tons of forms. I want you to know all of them, where you could answer, for instance, a matching question where it'd have like, entropy in any closed system will remain the same or increase. Total energy must be conserved, or total mass energy must be conserved. And then you go connect those with first law of thermodynamics, Newton's first law of motion, second law of thermodynamics, so on and so forth. So that's really all I'm trying to get from you out of 20. And then we're going to jump right into quantum mechanics, which I really wanted to do 3 chapters, but I don't think that's going to happen. We'll see. It's 37, 38, and 39 is the ideal scenario.
Okay.
I'm also going to try to make up a practice final exam and hopefully have that done by tomorrow, so you guys can start preparing for that. But the way I scheduled my final exam is the last week of school was Monday the 13th to Friday the 17th. You guys meet on Tuesdays and Thursdays, so I tried to make it on the Tuesday so you'd have one extra class day afterwards. In other words, you take it the earlier day in the week, so that should be on the 14th for your final exam. We're taking it by respondus like normal. If someone needs to take it some other way, please let me know ASAP. Like Monday is the latest, and then I could set it up at the testing center for you. But you should all take it during the regular class period. And I like always, I'll let you start up to say 45 minutes or even an hour early, because you will be allowed 2 hours, 2 hours 15, something like that, to complete it. So you can start early or start on time and finish late, going over. But if you start late, you're not going to get all the time. So if you start late, you're not going to get all the time, and you're not going to get more than all the time. So it'll be basically, it's going to stop you at 2 hours or 2 hours and 15, whatever I decide. I think it'll be 2 hours and 15. It'll stop you at that point, period, no matter what time it is. But if you started at, say, our class meets at 11, if you started at 11:15, you're only going to get 2 hours, period.
And once again, like with the midterm, there won't be a class that day. It'll just be the exam, and that's it.
Exactly. I might have some more. Well, I definitely have some more review sessions. I had, for instance, this week I did with my 241 students. I basically let them to attend any of my labs, and those labs were help sessions or review sessions. I'm probably going to do that next week with the labs as well, with your lab, so you can use that as a question and answer session. But it'll be student driven. You're not required to attend. If you come there, then you just should come there with questions specifically, hey, I don't understand this concept, or hey, I don't understand how to apply Newton's second, or well, in your case, it's I don't know how to apply, say, Gauss's law or Ampere's law, or specific questions from practice tests, specific questions from end of the chapter homework problems, or questions from the homework on mastering physics. Any of those things are fair game. I just want you to ask them so you can get help. Remember, this final is comprehensive, one, because it's really good pedagogy to have a comprehensive final, because it shows that evidence shows that when you study a whole length of a course and then go back and review that whole length of the course at the end, you retain that information better. And a lot of times you end up learning it better because your second time around, stuff makes sense that you didn't realize until you went through it the second time. So that's a good reason for a comprehensive final. The other reason is I try to give my students the opportunity to pass on the very last day, even if your grade's an F. And what I mean by that is, if I take and make a comprehensive final exam and a student scores, say, a 97 and a 98 on that, they've done a really good thing. And if I put that grade in and it says they still get an F, that student will probably not be given an F by me. Okay, I will almost certainly give them at least a C, but I might even give them an A. And that's just the way I do it, and I do it for everybody. So if you get a really high B, there's a good probability that I could give you even a B, but I'm definitely not going to let you get a D. Okay, so that's sort of my last life rope that I can throw you is, here's your chance. You screwed up. Yeah, you missed all your homework. You got zeros on all your homework. You've done pretty well on the test, but you're going to get a 80 at best if you scored all perfect hundreds. You can still get an A, though. All you have to do is do this well on the final without any suspicious, questionable looking behavior on your video. So be mindful of that. I did get a lot of pings this last time, and it was a pain in the butt. I had to go back and look at a lot of stuff. But when people are looking down like this, without, if you want to look down like that, that's perfectly fine, but you should do it like this, where I can see your eyes and I can see that you're looking at the paper and that you're not looking beyond this desk and you're writing stuff. That's what I want to see. I don't want to see you leaving the room. You have to show me, of course, your equation sheets, and we have that complete equation sheet in the documents now. That's all the equations from Giancolli's book. So that's automatically just done for you. You can just print it out and use that. If you want to add like my form of Coulomb's law, that's fine. That's why I made it up for you. You should be able to derive it yourself even, and in my form of Biot-Savart law, if you want to add that, that's fine as well. Any of those other equations that weren't numbered that I told you could use throughout the semester, you're allowed to use those. But remember, your equation sheet will be, held up so we can see it, turn it around so you can see the back, and show me, I'll pick up the camera and show me your work area so I can see nothing fishy's laying around. No phones. You have to have a dedicated scientific calculator that is not your phone. So just don't do any of that stuff, and then all that's fair game. Now, the other thing I gave you is that if you do better on the final, I will replace your midterm grade with that final exam grade. Okay. So that being said, that's it doesn't go the other way. So you want to make sure if you did badly on the midterm, which counts a big chunk of this grade, then you definitely need to look hard at doing well on the final.
But just to clarify, if something happens and we just completely bomb the final, but we did pretty well during the rest of the semester, we'll still be good. It won't be like if you do bad on the final, that ruins everything.
Well, yeah, I mean, I'm held to the grade system. I can give you only the lowest grade the grade system allows you to give, which is, if you look at the syllabus, I think the final exams are worth like 35%. So if you scored a 0 on that, the best you could get is a 65 for the course. So that's the crux of it. I mean, yeah. So if you do bad enough, it could make you fail. But if I look and most of your grades are pretty good, your midterm was good, all that stuff, and your grades coming up to a D, that's where it's going to get hard for me to decide whether I'm going to let you get that D or if I'm going to bump it up to a C. So I don't want you to completely fail or do horribly on the final because your grades are pretty decent. That's sort of the, counterproductive to your education. So please do your best on that. And we'll hope that you get, at least in the 50s or 60s. So I don't have to look at a chance of a student that was making an A all of a sudden getting an F.
I have one quick
I
question.
wish I could be nicer on that answer, but sorry. Go ahead. Is it Aiden?
Yep, Aiden. I have some classes that are switching up the test format on their finals. Will this be similar to the midterm with the computational portion and then a few larger
Yeah,
written
sometimes I
problems?
do concepts on the final. Sometimes I just do work problems where you're working out the solutions. But they're all going to be probably multiple choice. I might have a multiple choice where you have to immediately after taking it, take photos of your work and email it to me within 15 minutes of completing the test, something like that. And I might even have one where you have to do a calculation and type in the number for the answer. But I usually don't even do that. So it will be essentially the same format with or without concept questions. I'm not sure. I used to do 10 questions, but I've been leaning more towards 20 lately because students like having that many so they can make a few boo-boos. And what I normally do is about 80% of the points on the final will come from previous tests.
Gotcha. Okay, thank you.
No problem.
And if I remember correctly, I believe you said if there is any situation where we have to show you our work, it clearly states in the question that we have to send the work to you.
Exactly. So yeah, make sure you read the question because it'll have long, some of my questions look really long, but that's because I'm telling you, sometimes I'm literally telling you how to do it step by step, but I'm also including, hey, you got to turn this work in. So yeah, read the whole question, even if your ADD kicks in and says, oh, I'm going for crazy. Yeah, calm down and read it so you don't miss anything. I get into that sometimes with my ADHD, ADD stuff. I'll start reading something like, I'm getting really stressed out. I don't want to read this long. So I try not to make it that long, but sometimes that happens.
For easy reference, can you tell us exactly which chapters we're going after? Because I know that anything past 40 is extra credit.
Yes. So what we're looking at right now, and it depends a little bit on what I'm able to pull off next week, but what we're looking at right now is we did chapters, I think 21 or 22 is the one we started with. I can't remember, but starting at that chapter, we went all the way up to 31. Then we went back to 17, 18, 19, and just a skimming of 20. And then after that, I'll go to 37 and 38, but maybe even 39. Sometimes I do 37, 38, 39. I'll just make up a separate test for those and not put that on the final. So that's often a thing I'll do, but you'll see by the time I put up the practice final, you'll see whether that's the case.
So 21 to 31, and then 17 to 20, and then 37 to 38.
37, 38, and 39.
Okay.
That's ideally what I'm going through. By the way, I actually have those topics already on my YouTube channel. So if the homeworks are also up. So if you want to start doing that, you can at any time, and at least they're going to count as extra credit. But if they end up being chapters that we cover, then they'll be regular homework. But either way, you can start them already. Anything else,
I
anyone?
have a question.
Yes, Krisha.
So I have an exam the same day as yours, and I think they overlap. Is it like possible I could do it the next day?
I do, well, let me see. I'm gonna write that down. I'd have to make up a separate test for you. You only have one other exam at that time? On that day, I mean?
Yeah, ODU's exams, they give us 6 hours, and I won't take all 6 hours.
Oh,
but
yeah,
I
but
know
still, that's a brutal
it
test.
starts, yeah, it starts at 8:30 and it goes till like, I don't even know how long.
I know I can make it for the day before if you wanted, but I think I have a Wednesday time that you could do it. And if I remember correctly, let me see what's Wednesday. Yeah, we actually have an 11 o'clock slot on Wednesday that you could do it as well. So yeah, I can make it on Wednesday at the exact same time. I just have to make a separate test.
Okay, and is that on, wait, so was our test supposed to be on the 14th or the 16th?
Your test was supposed to be the 14th. Yeah, your Tuesday, Thursday class. So your class was supposed to be, your final was supposed to be on the 14th. I'm going to move it to the 15th, but it'll be named like Christian. It'll have your name in it, in the title, so you'll know which one to take.
Okay,
But it will be a respondus one.
thank you.
No problem. So that being said, everybody, remember, do not talk about what's on the test. The whole reason I try to get you all to take it at the same time is so that no one gets an advantage by hearing what's on the test and then taking the test. I will make a different test for her, but it's obviously going to have some similarities. So if you talk about it, then that gives her an unfair advantage, and of course makes me less likely to curve or anything like that I might have to do. So I know y'all not cheating in mind, but I just want y'all to think about that. Okay. So at least don't talk about it till after Wednesday. Anybody have any questions other than that? Okay, well, let's get started on this chapter 19, which we are almost done. I gave you those different conditions: adiabatic, isovolumetric, isochoric, isobaric, all that cool stuff. And I even showed you the ramifications of it. You know, like in an isobaric situation, the work's going to be the integral of PdV because it's a constant P. So that's just P times the change in volume is what the work is. Or if it's a adiabatic, then Q is going to be equal to 0 in the first law of thermodynamics. And don't forget also that we have this rule where our first law of thermodynamics is the change in internal energy is equal to the heat added minus the work, and this key word here, done by the system. Okay, so it's minus the work done by the system. If you're doing work on the system, then that work would be negative. So the minus and negative gives you a positive, and that should make sense, right? If you're putting work into the system, you should be raising its internal energy. Just like if you're adding heat to the system, you should be increasing its internal energy, which we figured out its internal energy really is basically the sum of all the potential and kinetic energies of the molecules making up the system. Molecules, atoms, whatnot. Does that make sense? All right, so let's start on doing some problems. And then we'll talk a little bit, hopefully, about chapter 20, so I can give you an idea of what that means. So first off, I'm going to consider an ideal gas. So this will be example 1. Consider an ideal gas. Now, we don't always have to say that. In fact, you pretty much can't solve these physics problems on gases and stuff like that unless you assume they're an ideal gas. So don't expect the word ideal to have to be in a question when you go to solve it for you to use the ideal gas law. If it's a sticky situation, and I mean that somewhat literally, if it's such a low pressure and low temperature that the molecular attractive forces between molecules or attractive forces between adjacent atoms comes into play, then obviously the ideal gas law wouldn't be applicable, and you want to look for something like the that other version, P minus something times V minus something equals nRT, Van der Waals equation. That's the one. But generally speaking, just remember that. So we have an ideal gas. And it's going to be compressed. At a constant pressure of 3.0 atmospheres from 11.0 liters to 2.0 liters. Then heat will be added. Then heat will be added to the gas, holding the volume constant. Until the temperature returns to its original temperature. And we want to know A, the total work done, what is the total work done by the system? Somebody came in, hold on a second. And B, what is the total heat added to the system? I should have typed this before, but I didn't. I had a meeting go right up to 2 minutes before class started. So, all right, so that's the big problem. And in fact, we could actually make a graph of this to make a little bit more sense. So what we have is I'm going to make a pressure versus volume graph. And what's going to happen here is we're first going to do a process where the pressure stays a constant. Is that right? Let's see, ideal gas compressed at a constant pressure, right? And the volume will go down. So I'm going to start right here. So this would be at some temperature TA, because I'm calling this the initial condition. And at constant pressure, it's going to do this. And it's going to go, of course, from 11.0 liters to 2.0 liters. And then it's going to go from that pressure, which was, of course, constant pressure of 3 atmospheres. So that's an ATM. And then it's going to rise with holding the volume equal to a constant. So it'll be a vertical line. And it's going to ride until it lands on what we call an isobar, or excuse me, isotherm. Sorry about that. And that is in fact going to be TB equal to TA. In other words, this is the curve for constant temperature, but we're going from here to here and then from here to here. And this goes from, in fact, 3 atmosphere to whatever the final pressure is. And we're not asked that, but we're going to figure out what the total work done is. Okay. So that's the actual process that we're going through. Yeah, I think that works pretty well. And remember, this is an isotherm. The equation for it, of course, is PV equals nRT, but T is a constant. So really you're doing P on the vertical axis is equal to N times R times T, which is a constant over V. Okay, so that's the equation, P equals some constant over V. So first thing we're going to do is try to calculate the work done. And in the isobaric situation, remember work is equal to the integral of P dV. In this case, the pressure stayed the same. So that just becomes P times the integral of dV, which really is just P times the change in volume, which is V final minus V initial. Okay. So this is work in, let's call this point C. So I'm going to say work from A to C. Now that pressure is going to be 3.0 atmosphere. And an atmosphere is 1.01 times 10 to the 5th Pascal. And then the change in pressure is going to in fact be from from 2 to 11, so it'll be 11.0 is the, no, that's the initial, sorry. So it'll be 2.0 liters minus 11.0 liters, like that. That's going to clearly give you a negative. But not only that, the Pascal is a Newton per square meter. So really this has to come out as a Newton meter. So this needs to be in meters cubed. So we know that in fact 1,000 liters is 1 cubic meter. So I have to multiply it by 1,000. So let's do that. So what I'm using here is a liter is supposed to be 10 centimeters by 10 centimeters by 10 centimeters. That's what a liter is. So 1 liter is equal to 1,000 cubic centimeters. Now, and that's centimeters cubed. So if you want to convert that to meters, you have to multiply by 100 centimeters in the bottom and 1 meter on the top, and you got to cube that. So you're literally going to divide it by 1,000,000. And that gives you 1,000 cubic meters, because 10 to the 2 to the 3rd power is 10 to the 6. So 10 to the 3rd divided by 10 to the 6 gives me 10 to the 3rd. So that's the conversion I used. So now I'm going to take this, work out the math. I will show you on my calculator so y'all can catch me if I make a boo-boo. So 3 times 1.01 e to the 5th times parentheses 2 minus 11 times 1,000. Actually, excuse me, got to divide by 1,000. I wrote it wrong. 1/1000. Sorry about that. Divide by 1,000. So I'll say 1 e to the negative 3, and that should work. And that gives me negative 2.727 times 10 to the 3rd joules. I really only put 2 sig figs in there, so these are extra digits. So that's how much work is done in that part. That's not the whole thing, of course. There's other work that's being done as well, but that's the first part. And then the total work done by the gas is going to be that that minus part there, which means is work done on the gas. And then we got to go from C to B. Work from C to B is equal to the integral of P dV. But in that case, we see that the volume is actually a constant. So the dV is equal to 0. So we end up getting 0 work done. So the work total is negative 2.727 times 10 to the third joules. And the negative implies work is done on the gas. Okay, let me circle this as a different color so we can see that's one of our answers. And then what is the total heat added? So what we have here is application of the first law. And the first law says that the change in internal energy dE is equal to the pseudo differential Q minus the pseudo differential W. So if we can figure out the final internal energy, we can figure out how much heat must be added. Okay. But because this ended up being an ideal gas, we know an expression already for the internal energy, and that is that the internal energy for an ideal gas is 3/2 nRT. So E.
We can't see what you're writing.
Thank you. E internal for an ideal gas is 3/2 nRT. And that's technically a monatomic gas. And I don't think, yeah, I didn't necessarily specify that. But the main thing that you need to see here is it's F times nRT, because the internal energy depends not only on the 3 degrees of freedom that come from moving of the center of mass of the atom / molecule in the X direction, Y direction, and Z direction, but it also includes possibly spinning about the X axis, possibly spinning about the Y axis, possibly vibrating this way, vibrating. So it ends up being like up to 9 different ways. But the main thing is you see that we went from TA to TB where they're the same. So the internal energy, this and this implies dE is equal to 0. Because the dE is equal to 0, then Q is equal to just d bar W. So in this case, we can say the heat added is negative 2.727 times 10 to the third joules. Again, I'm going to use a different color. And you could actually calculate what that temperature is if you wanted to. But the main thing is basically you're taking heat out of the system. Okay, because that negative indicates that. So those are 2 big things that you want to learn about the ideal gas law. I mean, about the first law of thermodynamics for your physics class, is that a negative W means work's done on the system, and a negative Q means heat taken out of the system. So any questions on that? Okay, so now we have to change gears a little bit, and y'all can work an example like 1911 if you want. That's pretty straightforward, but it's using that internal energy. The main thing to realize with the ideal gas law, the internal energy is just a function of the number of moles and the temperature. And then, of course, it depends on the number of, notice I used the F here, that's degrees of freedom. And what we mean by that is all the different ways it can have a 1/2 mv squared, or 1/2 I omega squared, or a 1/2 k x squared. So you can see for a monatomic gas, there's no way you can spin the atoms. You're not going to cause the atoms to actually spin with any appreciable moment of inertia, because atoms are supposed to be point particles in this scenario. So you really just get the 3 degrees of freedom from going in the X direction, the Y direction, and Z direction. But as you add, say, a diatomic molecule, you can see that I'm going to get 2 ways that can rotate. I can get, for instance, here like this, or I can also get here rotating through this axis, coming around. I'm trying to say it. Let's say this one's in this plane, so I'll do like this. So you can spin it about 2 perpendicular axes. So a diatomic, you're automatically going to get 5 halves. And then you get also, if the energy gets high enough, the temperature gets high enough, you can start engaging the atom, vibrating, and get that. This is all explained in a graph on page 513. So see graph on page 513, and I'm going to give you a drawing of that right now. But basically what we discover is this is kind of weird because it's a graph of something you don't know yet, but I'm doing as a function of temperature T, and I'm doing what's called the molar specific heat at constant volume. And we're going to say this is 4R, this is 2R, this is 1R, and this is 3R. And lo and behold, what we see is basically this would be, let's call this temperature 10,000. And it's in Kelvin. And we'll cut that in half and say that's 5,000. We'll cut that in half and say that's 2,500. And then of course we could break that down into 5. And each of those would be 500. So when you do this, what you see is it goes to about 75, basically, and it's running at about 1.5. And then when you get about there, it jumps up to 2.5. And then it goes on to about 1,000, which would be right about here. And then it jumps up at that 1,000 mark, it jumps up to 7 halves. Okay, what's going on here is you're just getting translational kinetic energy. Then you're getting from here and here, you're getting rotational, which is 1/2 I omega squared. And then from here to here, you're getting vibrational. Which is 1/2 kx squared. So that's what we're meaning. Basically, the energies don't kick in. These other forms, the I omega squared, don't kick in till you get well over roughly 100, or excuse me, 75. So I'm going to put this is down here is about 75 Kelvin is where that mark happens. And then this one's around, like I said, 1,000. This first one, yeah, comes up around 75. This one ends up right about 1,000 here, which I've got marked. And this is probably in the range of 300. So I actually drew this a little bad. This is actually in the range of 300. Okay. So that's just to teach you a little bit about how these atoms behave. Evidently, it takes a buttload of energy for you to make the atoms or molecules rotate, and then it takes even more energy to make them actually vibrate. So those things don't kick in all the time. So you don't always have, 7, 8, 9 degrees of freedom. In fact, this one only goes up to 7 degrees of freedom. Okay. So now that we have that sort of background on how things behave, I'm going to use this and try to show you, what time is it? Crap. Okay, I'm going to use this and try to show you a new derivation of things that are more useful. So we had Q is equal to MC delta T, where C is the number of calories per gram per Celsius degree. Well, we can introduce a new one where we're going to say Q is equal to N times C times delta T. Okay, and in this case, the capital C is equal to the number of calories per mole Celsius degree. By introducing that, we can actually make some really neat conclusions about physics. For instance, one, if you think about what we just talked about with those molecules and atoms, if you had, for instance, one at constant, let's say one at constant pressure, okay, so you're actually holding the pressure constant and you're trying to put heat into it. Well, holding the pressure constant basically allows energy to go into the 1/2 mv squared, obviously. But when you compare that to C again at constant volume, then you see, okay, well, it actually now has the ability to increase the pressure and therefore increase the speed by pushing out the walls of the container that it did there before. So you reach the conclusion that CP should be greater than CV. So let me show you what I mean by that. So if we have constant volume, then the second law of thermodynamics, or excuse me, yes, the first law of thermodynamics, and I don't know why I put a D bar E on that. That's supposed to be a regular D. If you have constant volume, then this has to be 0, right? So in this case, we get dq constant volume is just going to be equal to dE, the change in internal energy. Well, if you have it at constant pressure, then you have dE, and I'll subscript this V on that one, V on that one, P on this one. So now P on this one, that's funny. Okay, now I have dQP, and in this case, it's going to be minus P dV. So you see, when I have the constant pressure, some of the energy that you add can go into work being done. So not all of it goes to just the thing that raises the temperature. It also goes into work being done. So it's almost like it's a deeper reservoir. That's why you expect P to be larger than CV. So we now have that that's the case. And in fact, because it's constant pressure, you can now solve for QP. So D bar QP is going to be equal to DE plus P delta V, or P dV, I should say, since I'm using D's. So I've got DQ with constant volume is equal to DE with constant volume, whereas DQ at constant pressure is equal to DE at constant pressure plus PdV. Now I can start to think, what is the difference between QP and QV? So I'll do DQP minus DQP V, like that. When I calculate that, you can see I get DEV, because that's what DQV is, minus DEP minus PdV. It's minus and minus, so it should be plus. Okay. Well, the problem is DEV has got to equal DEP if we start and end at the same pressure, at the same temperature. So in other words, we're considering heating up of something, say from 10 degrees Celsius to 20 degrees Celsius. So the temperature change is just 10. Well, that means the temperature change in the volume case is 10, and the temperature change in the pressure case is 10. And we know that dE is only a function of temperature. So that means these two are equal. So we end up getting just P dV. So I'll say, but that'll make some sense out of that. Okay. So now that we got that, we can say, okay, well, wait a second. Let's go back to our definitions of dQp. What we're going to say is this is N Cp times dt minus N Cv times dt. And those dt's, of course, are the same. And that's P dV. Now, if I recognize dV from PV equals nRT, which suggests that V is equal to nRT over P, okay? And this, of course, came from the constant P1, then you know the only thing that changed was the temperature. So dV is going to be equal to nR dt over P. So now I can write N Cp dt minus N Cv dt is equal to N R dt over P. So you'll notice this N, this N, this N, this dt, this dt, this dt, they all cancel out. And by the way, I also had a P here, so that's going to cancel out as well. I forgot to write the P there. Sorry about that. So now I see that Cp minus Cv is just equal to R. So now we have a relationship. As we expected, the Cp is greater than Cv, and in fact, it's greater by an amount R. So this is a fundamental finding. And it turns out, even though we did this with ideal gases, it's really pretty darn straight. I mean, when you look at the experimental data, it turns out to be right. So that's kind of amazing. Now, if you take the ideal gas for instance, for a monatomic gas, so say we have a monatomic gas, then delta E, or let's just work with the E function as opposed to the change in E function. Let's just say E internal is equal to 3/2 nRT. And because of that, we can say, okay, well, E, the change in temperature internal is going to be 3/2 N times R times delta T. Well, if we consider the case where this is constant volume, then no work is done. So we can get that this would be equal to N Cv delta T. Now you can cancel out that again. And you see that Cv is going to equal 3/2 R. So this is another important result. Evidently, the specific heat at constant volume, the molar specific heat at constant volume, is 3/2 R. So I now can say Cp minus 3/2 R equals R. And then that implies that Cp is going to, I'll add this to both sides. That'll be 2/2 plus 3/2. This should be 5/2 R. And notice 5/2 minus 3/2 is actually equal to 2/2, which is 1. So now we've got another expression as well. So just from thinking out that process and using what we learned about ideal gas law, we can find out what the molar specific heats are. And they're just multiples of 5 of R, which is why I made a plot versus R over here. And you can see this is 1.5, so that's 3/2. That's 5/2. And of course, or excuse me, yeah, that's 5 halves, and then this is 7 halves ultimately. So we now have those neat, new, helpful results, and we can do some stuff with it. You've got new problems you can solve, things of that sort. But we also have something else we can do, because now we can consider the ramifications of having a adiabatic process. So let's look at adiabatic processes. I like using the differentials. So my first law of thermodynamics is always dE is equal to d bar Q minus d bar W. But in this case, what we're going to see is adiabatic means d bar Q is equal to 0. Adiabatic means it's basically insulated, or it happens so fast where heat can't flow. Those are the two ways you get an adiabatic process. But when you do have an adiabatic process, the Q is 0, so dE is just equal to the negative change in, or the negative of the work done. So we got dE is equal to the negative of the work done. And of course, the work done is negative PdV, like that. Now we can take the idea of working at a constant volume, and we'd say d internal for the same change, but for a constant volume, is just N times CV times dt. So if we combine these two, we can get a neat new scenario by looking at N CV dt minus P dV is going to be equal to, excuse me, I meant to say plus P dV is equal to 0. That's basically a type of differential equation that we can look at. If we take the differential of the ideal gas law now, you know, PV equals nRT, then what we could say is we could say P dV plus V dP is equal to nR dt. And with that, we can now take this NCV. Notice that NCV has a dt on it, and we can solve this for dt, so that dt turns out to be P dV plus V dP over N times R. I'm going to write this in here, P dV plus V dP over N times R. And then, of course, that's dP, and I had that plus P dV is equal to 0 again. So that was this equation, combining it with this stuff. Okay, again, this might not look so helpful to you, but you're going to see something come through in a second. Now what I'm going to do is multiply through by R with everything, and then distribute this. So I'm going to multiply both sides by R, which obviously for the right hand side is no big deal. That's still going to be 0. But when I do this, what's going to happen is NCV PdP is going to become NCV PdV over N, but notice the R cancels out. Okay. And notice now also that the N's cancel out here. So I got CV PdV, and that part's right. Now I'm going to do the same thing with the second term. So N CV times V dP, again over N times R. So I'll say plus N CV V dP over N times R. Again, this R is canceling out, and this N and this N cancels out. So I got CV V dP. And of course, all that's equal to, oh, I forgot a term, didn't I? Yeah. Plus PRDV. Wait a second, the PDV, when I multiply by R, that should have became R times PDV. Okay, yeah, that works. So I forgot part of this, plus R times P times dV, all that's equal to R. So what I want to do now is I'm going to get the terms that are in PDV together. So I'm going to write P dV. Notice that occurs here and that occurs here. So I'm going to say P dV times CV plus R right there. And then I have the other one is just going to be what's left, which is the CV V dP. And that's all equal to 0. Now that doesn't look very helpful, but watch what happens now. Remember, CV and CP are basically just a constant value for a given gas. So what I can do is take my expression for CP, sorry. I'm going to take my expression that CP minus CV equals R and realize that if I add CV and R together, then I get CP is equal to CV plus R, which is exactly what that is. So now I can say CP times P dV. Actually, I don't need to write that parenthesis at all. CP times PDV plus CV times VDP is equal to 0. Now what I'm going to do is I'm going to divide both sides by CV, and I'll get CP over CV, which is a new quantity we use, and we call it just gamma. I know that's another gamma for you, and that's kind of a pain, but anyways. We got gamma marking the photon. We got gamma marking the relativistic factor of 1 over the square root of 1 minus v squared over c squared. And now in thermodynamics, we have CP over CV is gamma. But that's going to be times P dV. And then now that we've divided through by CV, that CV is no longer there. So I'm just going to have plus VDP. And all that's equal to 0. Now what I can do is write this as dividing through by, let's multiply by 1 over PV. When I do that, notice I get the P canceling out and I'm left with a dV over V. So I'm going to say this is gamma dV over V. Plus, and this one, the V is going to cancel out and I'm left with dP over P is equal to 0, which when we integrate, we can see that I get, take the integral of both sides. You see the integral of dV over V is just going to be ln V. And then the integral of dP over P is just going to be ln P. So what I'm going to get is the ln of P plus gamma times the ln of V is equal to 0. And of course, that means you can write all this by making this an exponent on V, and you'd say the ln of P V to the gamma is equal to a constant. Oh, that should have been constant, by the way, not a 0. So what we've concluded is a very big important result, and that is P times V to the gamma power equals a constant. So one way we could write this is P1 V1 to the gamma power is equal to P2 V2 to the gamma power for an adiabatic process. So that's the big mother of all results that we wanted. And that's what we were doing all these crazy differential things for. If you ever take a thermo class, you'll see that the vast majority of thermo work is just a buttload of derivatives and comparing differentials to each other, just like I did there. So this is, I think it's pretty much like the book did its derivation. Actually, let me flip through. Yeah, they're doing essentially the same thing on page 514. And that gives you basically this new equation that we can use in addition to the ideal gas law, which, remember, the ideal gas law, if you have a fixed, if you have a collection of gas that's not allowed to escape at all, then the N and the R are clearly constant. So you get another nice expression, P1 V1 over T1 is equal to P2 V2 over T2. But if any of those variables are constant, you can just leave them off. So for instance, if you have a scenario where the temperatures are constant, then you just say P1 V1 is equal to P2 V2. Or if you have a scenario where the volumes are constant, then you say P1 over T1 equals P2 over T2. And of course, the same thing can happen if you use pressure being a constant. So these are just more tools we have. You can see plenty of examples. They're not that hard to solve. The only other thing I wanted to do in this chapter, and we've got plenty of time actually, the only other result that I wanted to give you in this chapter is about heat, conduction, transfer, and stuff like that. So it turns out that there's only more or less 3 ways which you can supply heat to something, and that is through conduction, which I'll remind you is touching, convection, and this is transfer via circulation. So for instance, 7-Eleven can now cook you a pizza in a really short period of time. That's because they're using convection ovens, and convection ovens basically have an intermediary, namely the air in the oven, and the heat of the actual burners or elements in there. And then they have a fan that blows over it, and that circulates the heat to basically all the parts of the pizza, and slowly, but more fast than normal, it actually cooks. And then the third way is radiation. Convection, as you can imagine, is really, really complicated. So we don't really have any expressions to offer there. But for conduction, we have a really nice expression. And it says basically the amount of heat added to a system divided by the time taken. Okay. So in other words, this would have units like of watts. So if I put a certain number of watts into some object, let's say the object looks like this. Okay, so let's say this is a hot reservoir and this is a cold reservoir over here. And what I mean by reservoir is basically this can keep pushing out heat forever, and this temperature is always going to say TH, and this temperature is always going to stay TC. In here is an area A, and from here to here is a length L. Well, it turns out that the amount of heat that can flow across this from the hot to the cold, which is, by the way, the second law of thermodynamics, heat flows spontaneously from high temperature to low temperature. That's one version of the second law of thermodynamics. You might want to write that down. Heat flows spontaneously from a hot object to a cold object. Well, it turns out this is equal to some constant, which is based on the material. So property K, some constant times the cross-sectional area. That makes sense, right? You would get warmer if you're on a cold day. If you've got a hot reservoir and you're trying to warm yourself up, if you lay your hand on it, that's going to feel pretty good. If you lay 2 hands on it, that's going to feel even better. If you maybe take your clothes off and lay on top of it, and you're not too bubbly like me, then then a lot of that surface area can touch the surface, and therefore the larger the area, the more heat that's transferred to you per unit time. So that should make perfect sense. And then finally, it's proportional to T hot minus T cold over L. So the longer you got to go, the slower it's going to take, or the more time it's going to take for the temperature to get from, or for the heat to get from here to here. So that's the convection equation. And this is, in fact, why that A being in there, that's why females tend to need wetsuits more than males. They have, you know, for two people of about the same height, a female will generally have more surface area than a male will, partly because there's a whole wider pelvic cavity that sort of, you know, makes it, well, what they would call childbearing hips, that sort of thing. That increases your area. And there's other ways, of course, that the female body has more surface area, but that larger surface area is exactly why scuba divers that are women tend to lose more body heat per unit time than a male diver will. Now, all bets are off. You talk to somebody like me, because I'm like a sphere up in there. So so A is quite big for me, so I lose a buttload of heat really quickly. That being said, I'm always hot, so I'd be happy for that. So that's the convection equation. Like I said, we don't really do anything, or excuse me, the conduction equation. I wrote convection, didn't I? Sorry about that. I didn't even realize I was writing that. It must have just read above it. That's conduction. You got to be touching. Notice the hot and the cold are touching this thing. So this is conduction. Sorry about that. Good Lord, I can't believe I did that. That's like the opposite of teaching. Okay. Now, it might also confuse you a little bit. If you go into a house and it's being built, you'll see that there's bats of insulation on the walls, and they'll have like R-13, or in some higher quality houses, you'll see R-19. And that's houses whose walls are 2x6 construction. And this is a house whose walls are 2x4 construction. Do not, if you want your house to be better insulated, you do not want to take your 2x4 walls, pull out the R13 and put in R19, because you'll actually make the R19 less than R13. So don't do that. It's the air that's trapped in the insulation that makes it so valuable. So you might say, hey, this number right here is conductivity. So how does that relate to R? Well, it turns out R is actually equal to L over K. So that length, the fact that it's a 19, shows you, hey, it's made to be thicker than the 13 is. And then the K, of course, is something they've determined experimentally from the fiberglass that they're using with the air spacing that they applied. So that's how those are related. Now, the other equation is the Stephon Boltzmann equation, and that's for radiation. And basically that says, so let me write radiation first so I don't screw up again. The Stephon Boltzmann equation. And that basically says what we call in astronomy luminosity, which is measured in watts. That is equal to, again, the delta Q over delta T. But in this case, it turns out to be epsilon times an experimental constant times cross surface area times T to the 4th power. This is the emissivity. I think it's 2 M's on that. Now I wanted to put like 14. No, it's 1 M. That's it. I wanted 4 M's. I want 4 S's. I want everything. Emissivity. Okay. For a black hole, for instance, this would be 1. That's a perfect conductor, but normally it's going to be something less than 1. This is the Boltzmann constant, which you can, of course, look up, but it's 5.67 times 10 to the -8. And that's watts per square meter per Kelvin to the 4th. And this is the surface area. And of course, the larger the surface area, the more stuff they can put out. That's why if you have a burner on your stove that looks like this, and another burner on your stove that looks like this, and then you have a pot of water that looks like that, and these are burners, you obviously want to put the pot on the big one. It wouldn't matter if the pot was this big, but with the pot being this big, you want to get as much of that on as possible. So that's what that says. It says that the heat sent out over a surface area A is equal to the emissivity of the thing times this constant times t to the fourth. So if you literally double the temperature of a star, for instance, you don't double, you don't quadruple, you don't 8-tuple. In fact, you 16-tuple the energy put out by the star. So that's another big law that comes in handy. And that's also the law that tells us if you take into account a human body and say in Scope or something like that, or in Chrysler Hall, any of those type of facilities, each person more or less acts like a 100-watt light bulb, which is why when you walk into an empty theater, it feels pretty good. But when the theater or the gym or whatever fills up, it starts to get really hot. Each human being in there is acting like roughly a 100-watt light bulb, because they're putting out this much heat at 100 watts, basically. And basically you use the temperature, that's got to be in Kelvin, by the way. You use the temperature of the body temperature, but it's also receiving energy from the room. So you have to say parenthesis body temperature to the fourth minus temperature of the room to the fourth. And you'll, lo and behold, using the typical surface area of a human, you'll get 100 watts. Okay. So that's another big equation that should be sort of studied. You should be able to do homeworks with this little description. And then finally, I want to talk to you about the second law of thermodynamics. I already mentioned one of them, and that was that heat flows spontaneously from a hot body to a cold body. So heat flows spontaneously from to T cold. Okay. In other words, if it's the middle of the summer and you've got your air conditioner on in your house, the hotter area is the outdoors. So if you left a window open or a door open, heat will be flowing. And even if you don't, because they're not 100% insulative, but the easiest case is imagining them being open, then heat will be flowing from the outdoor atmosphere into your house. You don't let the cold out, which is what mom says and what dad says when you complain about you leaving the door open. In fact, what's really happening is you're letting heat in. And that doesn't mean, for instance, an air conditioner can't work. An air conditioner can work, and it does, because you pay a power bill. The air conditioner takes hot temperature air, pulls the heat out of it, and delivers it to a hotter temperature. So you can make heat flow from hot to hotter. In other words, from cold to hot, but you have to add energy to it. So this is the second law of thermodynamics, one version. But like I said, there's a lot of different versions. Your book gives several of them in bold print. Another one is the Kelvin-Planck statement: is no device is possible whose sole effect is to transform a given amount of heat completely into work. So heat cannot be completely transformed into work. What I like to think of this is heat is a low quality type of energy. What heat is, remember, is that internal energy. It's the average random kinetic energy of all the molecules and atoms in there. So once you've got a certain amount of that heat, how hard is it to pull exactly that much heat out of all those atoms and molecules? it's almost impossible. So you're pretty much just going to leave some fraction of it to be wasted. And the drawing they normally do that is they'll say T hot for a hot reservoir. They'll show it going like this and then going into work, which would be this way. And there's T cold. This does not happen. Heat does not just flow in here and come out here. You actually have to have this is never zero. So that's the Kelvin-Planck statement. There's another one about Carnot engines, and it says all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. So basically, the Carnot engine is the most efficient, is another way of saying it. So I want you to reword this from your own books, but I'm just trying to give you an idea of what we're talking about. The Carnot engine is the most efficient. And no real engine can match its efficiency. Okay, so this is Carnot's theorem. So you've seen three versions now. The Clausius statement. So I'll have you look up the Clausius statement. I'm going to leave it blank, let y'all do that. It's kind of long for me to write. But basically it says no device is possible whose sole effect is to transfer heat from one system at temperature TL into a second system at a higher temperature TH. So that's sort of the same thing as we said earlier about flowing spontaneously. In other words, if you're trying to take heat from here to here, some of it's going to be wasted. And in that case, the waste is this part, and the stuff that you're getting for the air conditioner or the heater is the other part. The last part is about the entropy. And natural processes tend to move toward a state of greater disorder. Which could also be read as entropy. Okay, I would say the only real physical problem or mathematical type problem you should be able to solve for this is maybe example 20-9. And there was another one I like. Let me see. Basically, the other one is if you put, so let me stop looking at the page for a second. Let me turn on, we're about 3 minutes after. So if anybody needs to leave, I understand. I'm going to say this really quickly. So if you take a 100 gram chunk of metal and you put it into, say, a half cup of water, and the metal's at 100 degrees Celsius or 90 degrees Celsius or something like that, and the water's at 20 degrees Celsius, they're going to come to some equilibrium probably around 24 degrees Celsius or 22 degrees Celsius, something like that. Well, what about if I were to throw metal at 23 degrees Celsius into a cup of water at 23 degrees Celsius? Is it possible by the first law of thermodynamics for the metal to absorb enough heat to reach 90 degrees Celsius and the water drop to say 20 degrees Celsius? You'll see that the first law of thermodynamics does not violate that, is not violated by that. But if you calculate the entropy, where entropy ds, and that one's actually a real variable, so you can actually write ds as opposed to d bar s, ds is equal to d bar q over t. If you calculate the change in entropy, which is the heat added divided by the temperature, you could choose the average temperature, for instance, or you could do the integral. If you calculate the change in entropy, you'll see that second scenario where the heat is drawn from the 24 degree water or 22 degree water to heat up the metal to 100 degrees or 90 degrees Celsius. That's what's violated. So that's a very useful thing to do. I would say look up other two laws or second laws of thermodynamics and just know those, like memorize them word for word out of the book, not the versions I gave you, but the words from the book, and know their names, be able to do example 29 and see if you can do that problem that I just sort of outlined for you. Use calorimetry to see what would really happen if I put a 90 degrees Celsius block of aluminum in, let's say, and it's 100 grams, and we put it in, say, 500 grams of water at 20 degrees Celsius. What's the final temperature? And then try to work that backwards and see that you do not violate conservation of energy. In other words, the calorimetry works fine for it going from whatever that final temperature was, say 22, for it to go to 100 and to 20. But the entropy, in fact, does or is violated. So you actually have to decrease entropy. So I think that's enough. There's also other versions, like it's impossible to create a perpetual motion machine. That's a version of the second law of thermodynamics. Another version is it's impossible to reach 0 Kelvin. That's another version. And lo and behold, physicists have actually proven all these to be equivalent, but it's kind of amazing all the different ways you can apply it. So do a little deep dive, read the material, whatever, and do at least those two types of problems, and you should be more than covered for what's going to be on chapter 20. We'll start next time on chapter 37. Maybe I can do 37 and 38 in one fell swoop. I'm not positive of that. 39 is more like the quantum mechanics you do in chemistry. So if I don't get it, it's not a big deal. Y'all probably had it in chemistry. All right, folks, you're free to go. Thanks for coming. I'm sorry about running over about 6 minutes.
I wanted to ask,
Yes.
the lab is due at 1:55, the start of class for lab.
Yeah, I think
Right.
I did it a little bit later than the beginning of class. It's normally due at the beginning of class, but I think I did set it a little later this time on purpose.
No, I was meaning that it's currently set to 1 p.m. and I was
Oh.
asking is the actual due date at 1:55 when we start?
Oh,
Or
gotcha. Yeah, it's normally supposed to be at the start time, but I thought I had set it later. I might not have. So try to get it done by 1, but I'm probably going to set it back to like 1:20, 2 o'clock in case y'all need any help.
yeah, I'm doing it a little bit slow, so
No problem.
yeah.
All right. See you, folks.
See you.
Anybody else have any questions?
Hey, Professor.
Yes. Brett,
I actually do have a question. I had sent an email to you. It was probably quite a while ago. I just didn't want to bug you about it because I figured you were busy. The email was about the test 5.
Okay. Let me
I
write
had
this
actually
down.
missed the due date on that day, and then I think I emailed you saying, "Hey, I apologize. If there's any way I can at least just do it to get some credit for it." I don't know if you maybe have not received that email, but I was just still wondering.
I remember reading that, and I remember your name now that you said it. So probably I meant to do it and didn't, but test 5, you say?
Yeah.
And you're in 242. I'll set that up and let you do it. And since that took so long, I won't take off points. I'll just be nice.
Well, I appreciate that. Thank you very much.
No problem. Have a good one, Brett.
You as well.
Anything from you, Patrick? Hi, Patrick. My voice is too deep to do SpongeBob. I will. Have a good one, everybody. Bye-bye.